Hi everyone, my name is Pranshu Dumra and today I'll be presenting my project pitch for the Embedded Systems Development Unit. My project is Smart Grid System using automatic sun tracking solar panels. This solution combines renewable energy efficiency with embedded systems to create a reliable and scalable power management system. Let's move to the next slide. Here comes the problem domain. In many villages, electricity supply is either inconsistent or heavily dependent on fossil fuels. This not only harms the environment but also places a financial burden on households. While solar energy is widely adopted, most panels are fixed in place and lose up to 30 to 40% efficiency compared to sun tracking systems. An efficient automatic solar tracker can maximize energy retention, supporting essential services like schools, hospitals, and even small businesses such as agro-processing units. The challenge is to make such systems accessible and affordable for small-scale users. Now comes the gaps and the opportunities. Currently, small-scale users such as homes, farms, and rural communities lack affordable access to sun tracking solar systems. There is limited ability to monitor solar performance in real time and no easy way to manage multiple nodes and decide which one should supply power. The opportunity here is to design a low-cost embedded system prototype that combines automatic sun tracking, intelligent monitoring, and smart decision making to improve efficiency and reliability. Let's move towards the proposed solutions. My proposed solution is a smart grid prototype consisting of two Arduino Nano 33 IoT boards and one Raspberry Pi 4. The Arduinos will control the solar tracker, monitor battery levels, and send data. The Raspberry Pi will act as the central controller, making decisions about power supply and providing a backup power source if needed. Key features here include real-time monitoring of solar and battery performance, automatic selection of which node provides power, and an automatic fallback to the Raspberry Pi when both nodes are out of energy. The system is also scalable and can be extended to larger grids in future. So this is the block diagram. This block diagram illustrates the overall system architecture. Each solar panel connects to a charge controller and a battery. The Arduino Nano reads sensor inputs, controls the tracking motor, and communicates with the Raspberry Pi. The Raspberry Pi collects all telemetry data and decides which node should supply power and provides backup energy if required. Finally, the Raspberry Pi also hosts the user dashboard for monitoring and manual control. The main components of the system are the Raspberry Pi 4, which runs the MQTT broker and manages decision making, acts as the backup power provider, and hosts the web-based dashboard. The Arduino Nano 33 IoT, which reads LDR sensors for sunlight position, uses INA219 sensor for voltage and current monitoring, and controls servo or stepper motors for solar tracking. Connections include Arduino to Raspberry Pi via Wi-Fi MQTT, sensors to Arduino using analog and I2C, and motors controlled by PWM signals. Together, these interconnections allow the system to collect data, make decisions, and optimize power generation. Communication is a key part of the system. Between Arduino and Raspberry Pi, I'll use MQTT over Wi-Fi for telemetry and control. This enables scalability and integration with IoT dashboards. Within each Arduino node, the INA219 sensor communicates via I2C, while the LDR sensors use analog inputs and motors are controlled via PWM signals. As a backup option, USB serial can be used for debugging or direct communication. This combination of protocols ensures reliable communication across the system. The Raspberry Pi will host a web-based dashboard as the user interface. It will display each solar node's battery percentage, voltage, and current along with solar panel tracking angles. The interface will provide system alerts such as low battery or backup switching and it will also allow manual override, giving the user the ability to select which node supplies power. This makes the system not only automated but also interactive and user friendly. The system follows a continuous monitoring and decision making loop. First, each Arduino reads sensor data including battery charge and sunlight intensity and sends it to the Raspberry Pi. The Raspberry Pi compares the stages of charge between the nodes. If node A has more energy, it becomes the supplier. If node B has more, then node B becomes the supplier. If both are low, the Raspberry Pi comes forward itself and provides backup power. This ensures continuous operation and optimized energy use. The expected outcomes of this project include optimized energy capture, reliable power supply, scalability, user awareness, and sustainability impact, where sun tracking will improve solar efficiency by up to 40% compared to static systems. Smart switching ensures that power is always available even in low energy situations. The system can easily be expanded to include more solar nodes. The dashboard empowers users to track energy generation and consumption in real time, and by reducing reliable and reliance on fossil fuels and offering an affordable renewable options, the system supports cleaner and smarter energy adoption. In conclusion, this project demonstrates how embedded systems and smart grid technology can be combined to maximize solar efficiency while ensuring reliable energy availability. By integrating Arduino and Raspberry Pi with smart tracking and decision making, the system provides a scalable and affordable solution for small-scale renewable energy management too. This prototype lays the foundation for future smart grid systems that can empower communities with sustainable, cleaner and smarter energy. So this was my demonstration to this task. Thank you so much.